You've seen Saturn a million times in pictures and thought, yeah, we'll go there one day. But here's the punchline. For you, Saturn is basically off limits. Not because it's just far, but because it sits behind a wall of brutal distance, slow lightspeed delays, deadly radiation, and insane fuel demands. Robots have already made it, orbited, and even landed on its moons, but in this video you're going to see why, for human beings, Saturn is technically reachable, and still almost certainly out of your reach. Saturn orbits the Sun at about 1.4 billion kilometers. That's roughly 9.5 times farther from the Sun than Earth is. From Earth to Saturn, depending on where both planets are in their orbits, you're usually talking about something like 1.2 to 1.6 billion kilometers, around 750 to 1,000 million miles. That is the scale you are dealing with. Not thousands of kilometers, not millions, but over 1 billion. You can go all the way around Earth, again and again, tens of thousands of times, and you are still only matching that distance once. When engineers plan a Saturn mission, they are literally drawing lines across the solar system, not across a planet. Now, distance in space is not just a number you write in a textbook, it controls everything else. The time the journey takes, how much fuel you need, how much food and water you must carry, how long your hardware has to survive without major repairs. The farther the target, the more every small problem grows. On Earth, long distance means you refill the tank one more time. In deep space, long distance means you add years to the mission, and those years are full of risk. To see how extreme this is, look at the fastest thing in the universe: light. At Saturn's distance, even light starts to feel slow. A radio signal, which travels at the speed of light, takes around 70 to 90 minutes to go one way between Earth and a spacecraft near Saturn, depending on the alignment. When Saturn is around 9.5 times farther from the Sun than Earth, that one-way light time is about 79 minutes. That means if you send a command to a spacecraft, it sits in space for more than an hour before it even receives your message. Then when it replies, you wait another hour or more to get the response. Think about what that does to control. You cannot fly the spacecraft in real time. There is no joystick, no live steering. Everything has to be pre-planned, uploaded in advance, and then executed autonomously out there. If something critical fails at Saturn, by the time you hear "we have a problem," that problem has already existed for more than an hour. The gap is not just physical, it's a time gap in your ability to react. If the fastest possible signal is already that delayed, what happens with your normal vehicles, the ones you're familiar with? Take a modern passenger jet. It cruises at around 900 kilometers per hour, about 560 miles per hour. That is fast in everyday life. But if you tried to go from Earth to Saturn at that speed, and somehow you could fly in a straight line, non-stop, no refueling, it would still take well over 150 years. That is longer than a human lifetime. Even if you push that speed up by a factor of 10 to 9,000 kilometers per hour, which is far beyond what airliners do, you're still looking at a trip measured in many years, not days, not weeks. So normal aircraft are completely irrelevant here. They are too slow, the journey is too long, and that they could never carry the fuel, the oxygen, or the supplies for that kind of mission. Space to Saturn is not in the same category as any trip you make inside Earth's atmosphere. So what about rockets, the real tools for space travel? Look at Voyager 1, one of the fastest spacecraft we have ever launched. When it left Earth, it was moving at over 60,000 kilometers per hour, roughly 37,000 miles per hour. That is an extreme speed by human standards. At that pace, ignoring the details of orbits for a moment, a trip of about 1.2 billion kilometers takes more than 2 years. And that is for a relatively small robotic probe, not a huge, heavily shielded human habitat. This is the part most people miss. Fast in interplanetary space does not mean minutes or hours, it usually means years. A Saturn mission is a multi-year crossing of empty space. You accelerate, then you mostly coast. And during that coast, your engines, electronics, life support systems, and structure all have to keep working, without a safe harbour, without a pit stop. For a robot, that is already hard. For humans, it becomes extreme. Now imagine trying to send a crew. You cannot just copy the Voyager 1 profile and drop people inside. Humans need air, water, food, waste recycling, radiation shielding, medical supplies, sleeping areas, exercise equipment to fight muscle loss, backup systems and spare parts. All of that is mass. The heavier the spacecraft, the harder it is to accelerate, and the harder it is to slow down when you arrive. The trip time does not magically shrink, but the engineering requirements explode. And here is where distance becomes really brutal. Every extra kilometre multiplies your problems. You need more fuel, which makes the ship heavier, which means you need even more fuel just to push that extra fuel. Your navigation has to be more precise because small errors over billions of kilometres grow into huge misses. Your communication delay gets worse because light has to travel even farther. Your mission risk climbs simply because your spacecraft spends more time in a harsh environment with no rescue. This is why Saturn is not just Mars plus some extra distance. It is in a different difficulty class. Mars is tens of millions of kilometres away at its closest. Saturn is over 1 billion. That difference changes everything. Once you go beyond the asteroid belt and out toward the giant planets, you're playing a harsher game. The distances are so large that even small things like a tiny drift in trajectory, a slightly underestimated fuel need, or a minor hardware weakness can turn into mission-ending problems years later. So here is the question that really cuts to the core. If distance alone already makes Saturn this hard, why can't you just push harder, use a bigger rocket, and fly straight there like a long-haul shot into deep space? Why are missions to Saturn not just point the nose at the planet, fire the engines and go in a straight line? The answer is because in space you're not driving on a road, you're falling through gravity wells, and both Earth and Saturn are moving targets. You cannot draw a straight line, you have to drop from one orbit into another, and that completely changes how you travel. You can't just point a rocket at Saturn and go straight. You don't fly to Saturn like it's a road trip, you fall there. That sounds strange, but this is the key idea you have to accept or nothing about deep space travel makes sense. In space, almost nothing moves in straight lines. Earth is falling around the Sun, Saturn is falling around the Sun, and your spacecraft is just one more object dropped into that system. Right now, Earth is racing around the Sun at about 30 kilometers per second, around 19 miles per second. Saturn is also in orbit, moving at about 10 kilometers per second, around 6 miles per second, on a much larger path. You're not aiming at a fixed point in the distance, you're trying to move from one moving orbit to another moving orbit, while the central gravity of the Sun is pulling on you the whole time. Think of an orbit in a very simple way. You fall toward the Sun, but you're also moving sideways fast enough that you keep missing it, so you stay in a loop. When you launch a spacecraft from Earth, you are not leaving that system, you are changing which loop you are in. So when you say, why not just point the rocket at Saturn and burn in a straight line? What you're really asking is, why not fight the basic structure of orbital motion? If you tried to fly in a straight line, you would be constantly fighting the Sun's gravity, wasting huge amounts of fuel, and you would still end up on some curved path anyway, because gravity will bend your trajectory. The smart move is not to fight the orbits, it is to use them. That is where the most efficient trick comes in, the Hohmann transfer. If you want to go from Earth's orbit at about 1 astronomical unit out to Saturn's orbit at around 9.5 astronomical units, the fuel-efficient option is clear. You perform a burn near Earth to push your spacecraft onto an elongated ellipse, with its closest point to the Sun near Earth's orbit and its farthest point near Saturn's orbit. Then you basically turn the engine off and coast along that ellipse, falling through the Sun's gravity in a controlled way. When you finally reach the distance of Saturn's orbit, you fire the engine again to adjust your speed so you match Saturn enough to be captured, or to fly comfortably past it. On paper, this is clean and elegant, just 2 main burns, one to leave Earth's orbit, one to match Saturn. In reality, it comes with a brutal price: time. That kind of transfer is not a trip of hours or days, it is usually around 6 to 8 years of flight. That is the time scale where fuel efficient lives. If you say, We don't have time, let's just accelerate harder. With normal chemical rockets, you very quickly hit a wall, because carrying enough propellant to accelerate for long periods makes the spacecraft so heavy the performance collapses, so you accept the slow, precise arc. Because the alternative is not fast and easy, it is impossibly heavy and expensive. Now you might think, fine, if the path is fixed, at least we can leave whenever we want. Just launch on Tuesday or next month. But you cannot. There is another hard limit, the launch window. Because Earth and Saturn are both moving around the Sun, the relative positions of the two planets keep changing. For a Hohmann-type transfer, you need Saturn to be in the right place when you arrive, years later, and that means you must launch at a very specific time, when a line from Earth to where Saturn will be lines up with your transfer orbit. Those configurations do not happen every week. They show up as specific windows separated by years. If you miss the ideal window and you launch much earlier or later, your spacecraft has to do extra work, meaning more change in speed, which means more fuel, which means more mass. In practice, for certain profiles, missing by even a month can push you out of the best geometry. Then your options are ugly. Either you accept a longer, less efficient flight, or you skip this opportunity and wait for the next alignment, which might be many years away. When you hear mission planners talk about we had to make this launch date, this is what they mean. The solar system does not care about your schedule. But even when you hit the right window and you use a good transfer, chemical rockets alone are often not enough for ambitious missions. So engineers use another tool, gravity assists. This is where you fly past a planet like Venus, Earth or Jupiter, and you steal a little bit of its orbital energy. You approach the planet on a carefully chosen path, you swing around it, and gravity bends your course and tweaks your speed. From the spacecraft's point of view, it gets a big change in direction, and sometimes a huge boost in speed, without burning a lot of fuel. Cassini, the famous Saturn mission, did not just go Earth to Saturn in one clean shot. It followed a complex path with flybys of Venus, Earth and Jupiter, each one timed to the hour. Every pass changed its trajectory and speed by thousands of kilometers per hour, thousands of miles per hour for free in terms of fuel. But that free speed comes with a cost in planning and rigidity. Once you commit to that sequence of flybys, you are locked into a long chain of events stretching across years. You cannot casually cancel a flyby or move it by a week, because the whole geometry of the orbit, the timing, the position of the planets, all of it is tied together. And here is where it gets really unforgiving. Once your trajectory is set, once your spacecraft is on that interplanetary arc, changing your mind is extremely expensive. Small corrections are fine. You can adjust your speed by a few centimeters or meters per second to clean up your targeting. That is within normal propellant budgets. But big changes, like hundreds of meters per second, are a different story. That kind of change means tons of extra fuel which you had to launch from Earth at the very beginning. If halfway to Saturn you suddenly decide, let's go somewhere else, the answer is, in most cases, you can't. For a human mission, this locked-in trajectory is a serious problem. Once the crew leaves, they are committed to a path that plays out over many years. There is no quick return, no sudden diversion to another planet, no simple abort and come home. The solar system is not a highway network where you can take the next exit. It is a set of deep gravity wells and narrow timing windows, where almost everything important has to be decided before the rocket even leaves the ground. So now stack this on top of what you already know. Saturn is extremely far. The paths you are allowed to use are long, curved and slow, and the timing is rigid. That leads to a brutal next question. If the geometry and timing are this strict, what happens when you try to squeeze more performance out of your rocket to buy back speed and flexibility with raw power? That is where the physics of the rocket itself starts to fight you, and the rocket equation turns your Saturn dream into a losing battle. You probably think the fix is simple, just build a bigger rocket, burn more fuel, go faster and crush the distance problem. But this is where the universe hits you with a hard rule. The laws of physics tax every extra kilometer per hour you try to squeeze out of your rocket, and that tax grows brutally the faster you want to go. This isn't about lazy engineering, this is baked into how rockets work. There is a basic idea in rocketry called change in velocity, usually called delta V. It's not your speed at one moment, it's how much total speed change your rocket can deliver over the whole mission, all the burns added together. The rocket equation says your total change in speed depends on two main things: how fast your exhaust leaves the engine, and how big the ratio is between your full rocket and your empty rocket. But here is the catch: the mass ratio sits inside a logarithm, which, in plain language, means you very quickly hit diminishing returns. Doubling your fuel does not double your delta V, it gives you a much smaller increase, and every extra bit of performance costs more and more fuel. This is the Tsiolkovsky trap. If you want just a little more total speed change, your fuel mass does not go up in a nice straight line, it explodes in a steep curve. For something close like low Earth orbit, you can live with that. For something far like Saturn, where the total delta V bill is enormous, the curve destroys you. Every extra kilometre per second you ask for is like asking the universe for a loan at a terrible interest rate. The debt grows faster than you can sensibly pay it off with chemical fuel. And here's the next problem. Your main tool, the chemical rocket, is already close to its practical ceiling. The best chemical engines we have today throw exhaust out the back at around 3 to 4.5 kilometers per second. That's about 6,700 to 10,000 miles per hour. That number is your exhaust speed, and it caps how much delta V you can reasonably get from a single stage. In practice, a well-designed chemical stage might give you around 9 to 10 kilometers per second of useful total speed change before it's out of propellant. Now, look at what you need just to get started. To sit safely in low Earth orbit, you already had to accelerate to about 7,800 meters per second, around 28,000 kilometers per hour, roughly 17,500 miles per hour. To escape Earth's gravity completely, you need a bit more, roughly 11.2 kilometers per second relative to Earth, about 40,000 kilometers per hour, around 25,000 miles per hour. That means just climbing out of the gravity well and reaching a useful starting point for a deep space mission already eats most of what a single chemical stage can deliver. That's why real launch vehicles stack stages, like nested layers, each one emptying and dropping away to let the next one fire. For Saturn, that stacking becomes extreme. You need stages to get to orbit, stages or stages plus upper stages to push you onto a transfer out toward the outer solar system. And then, if you want to actually stop at Saturn instead of just racing past it, you need more propulsion to slow down when you arrive. You end up designing a system that is basically stages on top of stages, with a small useful payload riding at the very top of a huge assembly that is mostly fuel tanks. Now add the nastiest part of all: every kilogram of fuel you plan to burn near Saturn has to start on Earth. To deliver that 1 kilogram to the outer solar system, you have to launch it from the surface, accelerate it to orbital speed, maybe push it through multiple burns and gravity assists, and keep it stable for years. That means you burn fuel to carry fuel, which will later burn to carry more fuel. The rocket at liftoff is almost all propellant, a little structure, and a tiny fraction of useful cargo. If you scale that up to a human-rated Saturn mission, it gets absurd. You need propellant for the main interplanetary burns, extra propellant for course corrections, extra for braking at Saturn, maybe extra again for leaving Saturn orbit and coming home. On top of that, you need the large, heavy habitat, life support, shielding and supplies. By the time you stack all of that, the launch mass is so huge that it is beyond anything we have ever built or even seriously funded. And Saturn's delta V bill does not care about your budget. From low Earth orbit, you need enough delta V to escape Earth's gravity, to shape your path outward, to pass the orbits of Mars and Jupiter, and then, if the goal is to stay, to slow down so Saturn's gravity can capture you instead of just letting you slingshot away. If you add up all those steps, including safety margins, you are looking at total delta V in the tens of kilometers per second. That is brutal for chemical propulsion alone, unless you invent in space refueling depots or extremely advanced high-performance stages that we have never flown. To get a sense of how extreme these numbers are, compare them to speeds you understand. A fast sprinter might run at 10 meters per second, around 36 kilometers per hour, about 22 miles per hour. That feels quick when you watch it on a track. Low Earth orbit needs about 7,800 meters per second, so almost 800 times that sprint speed. Transfer paths and capture burns for Saturn push you several thousand meters per second beyond that again. Your rockets are trying to stack thousands of human running speeds on top of each other, and each extra stack costs more fuel than the last. And remember, this is all before you add the reality of flying humans, who cannot be squeezed into a tiny capsule with no room, no protection, and no redundancy. The rocket equation is already punishing you en masse before you add radiation shielding, spare parts, food, water, oxygen, exercise gear, medical equipment, and all the safety systems you would want for a trip that lasts many years. When you add those, your mass goes up, your required fuel goes up even more, and the whole design starts to break under its own weight. So here is the question that should make you uneasy. If the physics of rockets already make Saturn feel almost out of reach for machines, what happens when you put fragile human bodies inside that metal shell and send them into deep space for years straight, away from Earth's shield, away from quick rescue, soaked in microgravity and radiation the entire time? Getting to Saturn is not a road trip. It is years in an environment that slowly dismantles your body and your systems. Distance and delta are one thing, but once you put humans inside that metal can, the whole mission changes. You're not just moving mass through space, you're trying to keep fragile biology functioning for a time span that pushes right up against what we know how to manage. Start with the basic problem, gravity, or rather the lack of it. In low Earth orbit on the ISS, astronauts float in microgravity, and we already see serious damage. Even with more than 2 hours of hard exercise every day, they lose bone density and muscle mass. In the weight-bearing bones, like the hips and legs, you can see bone loss of about 1 to 2% per month over 6 to 12 months. Muscle shrinks, the heart does not have to push against gravity, so it deconditions, blood volume drops. That is in a place only about 400 kilometers up, where you can be back on Earth in a few hours if something goes wrong. Now stretch that to a Saturn mission. You are not talking 6 months, you are talking 6 to 8 years just for the flight. Plus whatever time you spend in the Saturn system. Multiple years away from real gravity. Even if you keep up strict exercise, you're asking the human skeleton, the cardiovascular system, and the muscles to tolerate conditions they were never built for far longer than any current mission. When that crew finally tries to walk again on a moon, or even stand up in a partial gravity environment, their bodies could be dangerously weak. You're basically planning to send people out, knowing that everything that supports their movement and their heart function will be under constant long-term stress. Then add radiation, which does not care how disciplined you are. Close to Earth, our magnetic field and atmosphere block most of the high-energy particles from space. Once you leave that shield, you are exposed. There are galactic cosmic rays, which are high-energy particles coming from outside the solar system, and there are solar particle events, sudden bursts from the sun, like during solar flares and coronal mass ejections. Probes on the way to Mars have already measured radiation doses that are a concern over just a few months. Now scale that exposure up to 6, 7 or 8 years in transit to Saturn, plus time in orbit there, and you start stacking up serious cancer risk and possible acute radiation problems if a big solar storm hits at the wrong time. To deal with that, you need shielding. Shielding usually means mass, thick walls, water tanks in the right places, maybe specialised materials. For a short mission, you can design a compact storm shelter inside the ship. For a decade-scale mission, you need the whole living area to have meaningful shielding, because you cannot tell the crew to spend most of their lives in a tiny bunker. Every extra centimetre of material around them increases protection a bit, but it also adds weight, which pushes your rocket equation in the wrong direction. Now look at life support. On a weekend trip in a car, you bring a couple of bottles of water and some snacks. On a short space mission, you can load consumables for the whole flight. On a Saturn mission, every extra month means more air, more water, more food, more spare parts, more filters, more chemicals for carbon dioxide removal, more replacement components for pumps and fans. You cannot just store 10 years of everything, the mass would bury the mission. So you turn to recycling systems, closed-loop life support, where you clean water, scrub the air, maybe grow some food. But closed-loop systems are not perfect. Filters clog, bacteria grow where they should not, sensors fail, pumps seize, valves leak. Over a few months you can handle that with spares and maintenance. Over many years, you need redundancy on top of redundancy. You need backup machines for your backup machines. You need tools, 3D printers or machining capability to fabricate replacement parts, diagnostics to spot problems early. All of that means more equipment, more complexity, more mass. The longer the mission, the more your life support system turns into a small, fragile ecosystem inside a metal box. And every failure mode has to be anticipated from the start because you cannot call a repair team from Earth. Then there is the part people like to ignore because you cannot see it on a diagram, the mind. You lock a small crew, maybe 4 to 6 people, inside a volume roughly comparable to a modest house or apartment complex for close to a decade. There is no real time conversation with Earth. Every message takes over an hour one way near Saturn. There is no option to say I'm done, I want to go home, because going home is another multi-year trajectory. On the ISS, astronauts can see Earth out the window, they can talk with family with only a slight delay. They know that in an emergency they can be back on the ground in less than a day. That station is only 400 kilometers up. Saturn is over 1 billion kilometers away, hundreds of millions of miles, and psychologically that is a different category of separation. You have to assume long-term stress, tension inside the crew, sleep disruption, anxiety, maybe depression. You have to maintain discipline, technical performance and good decision-making in a place where every argument, every mistake happens under conditions that never stop being hostile. You can use training, careful crew selection, virtual communication, smart interior design, but you are still asking human minds to carry a load we have never really tested at that timescale, that far from help. And finally, you remove the one comfort every current astronaut still has, the ability to abort. On a trip to the moon, you can turn around and come back in a few days. On a trip to Mars, you can at least imagine a high-energy abort that swings the ship back toward Earth in months if you're willing to accept extra risk and extra fuel. To Saturn, once you commit to that transfer, turning around is essentially another Saturn-class mission in reverse, another arc of years. If something critical fails in year 3, there is no station in between where you can park, there is no rescue ship coming, there is no safe harbour. Every system you launch with has to be strong enough, repairable enough and redundant enough to survive without support for a huge fraction of a human working life. So ask yourself, if deep space spends years trying to grind down your bones, your muscles, your nervous system and your hardware, what happens when you finally arrive at Saturn itself, a giant planet with its own magnetic field, radiation belts, and harsh local environment that were never designed with human safety in mind? You escape Earth's radiation belts, only to aim straight for Saturn's. You get out from under our planet's magnetic shield. You cross deep space, taking hits from cosmic rays the whole way, and then, right when you arrive, you dive into another giant magnetic field that has been trapping charged particles for billions of years. You're not arriving in a calm, empty place, you are parking next to a huge natural radiation machine. Saturn has its own magnetosphere, its own magnetic bubble carved out of the solar wind. That magnetic field traps protons and electrons and shapes them into radiation belts, a bit like Earth's Van Allen belts, but spread over a much bigger volume. They are not as extreme as Jupiter's, which are instantly lethal without very heavy shielding, but less intense than Jupiter still means harsh. For sensitive electronics and long missions, dose rates near some parts of Saturn are high enough that you cannot ignore them. You have to design around them from the first sketch of the spacecraft. Every one of those trapped particles is a problem for your hardware. High-energy protons and electrons slam into the materials of your spacecraft. They knock atoms out of place and they generate secondary radiation inside the walls. In your electronics, a single particle can flip a bit in memory, corrupt a calculation, or in the worst case trigger a latch-up that burns out a component. Over time, the constant hits slowly degrade chips, sensors, and solar cells. To cope with that, you harden components, you use special manufacturing process, you add physical shielding, and you write systems that can detect and correct errors. You build in redundancy so that when one box dies, another one can take over. All of that extra protection adds complexity, adds mass, and pushes the cost up, just so the spacecraft can stay functional in Saturn's neighbourhood. Now think about cumulative dose, not just instant hits. An unmanned probe can tolerate a certain total amount of ionizing radiation over its lifetime before the risk of failure becomes too high. A human body is the same, but the limits are much stricter. By the time a crew has spent 6 to 8 years flying through deep space, they will already have taken a significant radiation dose from cosmic rays and solar particles, even with decent shielding. If you then park that crew in Saturn orbit for months or years, flying repeatedly through parts of the magnetosphere with higher radiation, the total dose climbs further. To keep that dose in a range that is not completely unacceptable, you need heavily shielded living areas, not just thin walls. Here is where the numbers turn nasty. To cut radiation significantly, you add shielding measured in grams per square centimetre, which is basically how much mass sits in front of each square centimetre of surface. Something like 10 grams per square centimetre of extra shielding might mean on the order of 10 centimetres of water, or a few centimetres of a heavier material. Wrap that thickness around a large crew module, and the added mass quickly reaches tens of tons. Every ring of shielding around a habitat means more tons in your launch manifest, more structure to hold it, more propulsion to assist. Propulsion to push it all the way to Saturn and slow it down when you arrive. And Saturn's moons do not all sit in the same safe zone. Some of the interesting ones scientifically, like Enceladus and Dione, orbit in regions where radiation levels are noticeably higher. Enceladus with its water plumes is a prime target for exploration, but it is also sitting inside parts of Saturn's magnetosphere where charged particles are more concentrated. A long-term human stay on a moon inside those belts is basically asking a crew to live next to a slow, invisible particle accelerator. The dose might not kill you in days, but over months and years it adds up in a way that you cannot ignore. You either accept a high health risk, or you bury your habitats under thick layers of local ice and rock, which is a whole different construction problem. Some moons, like Titan, have a thick atmosphere that helps block radiation at the surface, which is one of the reasons Titan looks slightly more promising for human presence. But that does not erase the exposure during transit, during orbital operations, and during moves between moons. You still have to cross belts, you still have to design vehicles and stations that can handle the environment while they are in orbit or flying through the system. All of this feeds straight back into the rocket equation you're already losing to. More shielding means more mass. More mass means you need more delta V to accelerate and decelerate the spacecraft. More delta V means more fuel. More fuel means bigger tanks and stronger structures. Bigger tanks and structures mean even more mass again. It is a feedback loop. The need to protect human tissue and sensitive electronics inside Saturn's magnetosphere is directly fighting your ability to even get that spacecraft there in the first place with chemical rockets. You can try clever tricks, like concentrating the shielding into a smaller storm shelter volume where the crew can hide during solar events, while accepting higher but still tolerable background levels in the rest of the ship. That reduces mass, but it does not solve the long-term problem. For chronic exposure from cosmic rays and trapped particles, you want the main living areas shielded all the time, not just during a flare, so you are stuck choosing between underprotecting the crew and overloading the rocket. So step back and look at the situation. Deep space gives you constant radiation for years. Saturn adds its own belts on top, and your only real defense is thick, heavy material that your already stressed rocket has to push for billions of kilometers. And that is before you even talk about the next layer of difficulty, the basic environment. Because even if you somehow manage the radiation, you still have to keep the ship powered and warm in a region where sunlight has dropped to around 1% of what you get near Earth, and the temperatures push materials and propellants toward their limits. If radiation is already forcing you to add mass and complexity, what happens when you also have to deal with cold so deep that water is rock? Methane behaves like a liquid, and the sun is barely more than a bright star, while your spacecraft still needs kilowatts of power and stable temperatures just to keep people alive. Saturn is so far from the sun that both your fingers and your spacecraft's power budget go numb, and I mean that literally. Close to Earth, sunlight is strong, solar panels make sense, warmth is something you mostly have to get rid of. Out where Saturn lives, light is weak, heat is rare, and everything you normally rely on for power and temperature control starts to fail. Near Earth, at 1 astronomical unit, you get the full strength of the Sun. At Saturn, around 9 to 10 astronomical units out, that intensity drops to roughly 1/80th to 100th. In simple terms, if you have a solar panel near Earth that gives you 10 kilowatts of power, enough to run a decent-sized house, the same panel out near Saturn would make maybe 100 to 130 watt. That is the kind of power you use for a bright light bulb or a laptop, not for a full life support system, not for big communication dishes, not for electric propulsion. To run a human ship on solar out there, you would need absurdly huge solar arrays, many times larger than anything we have flown, and every square meter adds more mass and more surface area that micrometeoroids and radiation can damage. That is why Cassini did not bother with solar panels. It used radioisotope thermoelectric generators, RTGs, devices that take the heat from radioactive decay and turn a small part of it into electricity. For an unmanned probe that works, you do not need megawatts, you just need a steady few hundred watts for instruments and communications. For humans, that is nowhere near enough. A crewed Saturn mission needs kilowatts to tens of kilowatts just for life support, lighting, circulation fans, computers, communication, environmental control, maybe artificial gravity systems, and if you want advanced propulsion, you need far more. That pushes you from RTGs into the realm of actual nuclear reactors in space, running steadily for years. And nuclear reactors create their own stack of problems. You have to launch nuclear fuel from Earth, which brings fights and safety requirements. You have to design a reactor that can run for a decade without hands-on maintenance. You have to shield the crew from the reactor's radiation while still letting heat out. You have to make sure the system is safe if the rocket fails early in flight. None of that is trivial, and we have almost no experience flying large, long-life space reactors. But at Saturn distances, nuclear power stops being a nice advanced option and becomes almost mandatory if you want a serious human mission. Then there is the environment itself. Saturn's upper atmosphere is around minus 140 degrees Celsius, roughly minus 220 degrees Fahrenheit. On Titan, the big moon, the surface temperature is about 94 Kelvin, which is minus 179 Celsius, around minus 290 Fahrenheit. At those temperatures, water is rock hard. Methane, which is a gas in your kitchen stove, behaves like liquid water on Titan. Metals contract, some materials become brittle, lubricants can freeze or stop working the way they should. Every bearing, every hinge, every seal has to be chosen and tested for cryogenic conditions, not just for a few hours, but for years. Your spacecraft has to live between two extremes. Inside, humans want something like 20 degrees Celsius, room temperature, maybe a little cooler or warmer. Electronics also like a comfortable range, not too hot, not too cold. Outside, space near Saturn is only a few degrees above absolute zero, and when you're in shadow you see almost no sunlight. If you add a nuclear reactor to this system, you now have a strong heat source bolted onto a ship floating in a deep freeze. You must keep people and machines warm, while also dumping the excess heat from your power systems into an environment that is very bad at accepting it. In space, you cannot use air or water around you to carry away heat. You rely on radiators, big panels that glow in infrared and slowly leak energy into the background. For a powerful reactor, those radiators must be large. Large radiators are heavy, they are awkward to unfold, and they are vulnerable to impacts and damage. If a micrometeoroid punches a hole in one, you lose cooling capacity. If your radiators are undersized, the inside of your ship overheats, which is just as deadly as freezing. Thermal control becomes a constant balancing act. and the hardware to do it well adds more mass and more failure modes. Now think about propellants, the fuels you need for course corrections, orbit changes, and possibly landing or takeoff from moons. Some of the best performing fuels, like liquid hydrogen, must be kept extremely cold to stay liquid. Over long durations, even with good insulation, they slowly boil away. On a multi-year mission, that slow boil off can drain a huge fraction of your fuel, unless you add active cooling, which again takes power and equipment. Other fuels, hypergolic propellants, are more stable and can sit in tanks for years, but they are toxic and they're heavier and less efficient in terms of energy per kilogram. Some propellants can actually freeze in deep cold, clogging lines and valves. Every choice you make is a compromise between performance, long-term storage, safety and mass, so you end up in a loop again. Saturn is dark, so you go nuclear, which gives you heat you then must get rid of. Saturn is cold, so you design hardware for cryogenic temperatures, which makes everything more complex. You need propellant that will still be usable after years in that cold, so you accept worse performance or add heavy cooling systems. Every fix you bolt onto the design makes the rocket equation worse, adds more mass to push across those billions of kilometers. And remember, this is not just a drifting bunker. You still have to point it, steer it, and talk to it from Earth, across a distance where light itself takes more than an hour to cross one way. You'll be trying to navigate a massive, fragile, hot on the inside, frozen on the outside nuclear-powered ship through a system of moons and rings, while the signal between you and mission control crawls along with a huge delay and gets weaker every kilometer. So here is the next question you have to face. If the environment is this cold, this dark, and this demanding on your power systems, how do you actually steer precisely and communicate reliably with something at Saturn, when every tiny navigation error can grow into millions of kilometers, and every message takes more than an hour to get there? At Saturn, you are steering a bullet blindly and talking to it on a 90-minute delay, and that is not an exaggeration. That is just how the physics works at those distances. By the time a signal leaves Earth, crosses more than 1 billion kilometers, and reaches your spacecraft, the situation on board has already moved on. You are always working with old information, always reacting late. Start with navigation, because if you cannot point the ship where it needs to go, everything else fails anyway. When you launch towards Saturn, you set up a trajectory and then you coast for years. During that long coast, tiny errors grow. A velocity error as small as 1 millimeter per second, that is 1,000th of a meter per second, sounds like nothing. You would never feel it in a car. But multiply that tiny drift by years of travel, and it can turn into tens of thousands of kilometers of missed distance by the time you reach Saturn's orbit. At solar system scales, almost perfect is not good enough. To keep that under control, navigators do not rely on one method. They use radio tracking, measuring tiny shifts in the frequency of the radio signal called Doppler, to figure out how fast the spacecraft is moving along the line between Earth and the probe. They use star trackers, cameras that lock onto patterns of stars to know exactly which way the spacecraft is pointing. They use optical navigation, taking pictures of Saturn and its moons against the background stars, and then comparing those images to precise models to see where the spacecraft really is. All of this data comes back to Earth, gets processed, and then engineers plan small engine burns, maybe changing the speed by a few centimeters per second to trim the path and keep the spacecraft on target. With a robot, you can accept that slow, methodical loop. Measure, compute, correct. With humans on board, every correction burn is happening around people whose lives depend on that path being right, and you are still doing it with information that is always at least an hour out of date. Now, layer communication on top. A spacecraft near Saturn is sending a radio signal so weak by the time it reaches Earth, it is billions of times fainter than the signal from your phone to the nearest cell tower. To hear it, you need massive antennas on Earth, like the 70-meter dishes of the Deep Space Network. Those dishes stare at a patch of sky, pick up a whisper of radio energy, and use sensitive receivers and long integration times to pull the data out of the noise. That whole setup exists just to pull a trickle of information off a probe on the other side of the solar system. The distance also sets the delay. At Saturn, depending on where Earth and Saturn are in their orbits, the one-way light time is around 70 to 90 minutes. That means every command you send takes over an hour to arrive. Every status message you get back left the spacecraft more than an hour ago. There is no way around that. You cannot cheat the speed of light. So you cannot fly the spacecraft like a drone. You cannot joystick it. If you try to steer in real time, you will always be acting on what the spacecraft was doing a long time in the past. Because of that, every important maneuver has to be planned in detail, simulated on the ground, and then uploaded in advance as a sequence of commands. The spacecraft then executes that sequence on its own, using its computers, sensors, and guidance systems. If something unexpected happens in the middle of a critical burn or during a close flyby, you're not there with your hands on the controls. You only find out after the event is already finished, when the telemetry finally crawls back to Earth. Then there is pure data rate. You're used to home internet connections that run at tens or hundreds of megabits per second. You can stream video, download gigabytes of data in minutes. A probe at Saturn, using a high-gain antenna and a powerful transmitter, might get a data rate of a few kilobits per second, maybe tens of kilobits in the best conditions, which is thousands of times slower than what you have at home. That shapes everything. You cannot send huge amounts of raw video and high-resolution data all the time. You compress, you pick and choose what to downlink, you accept that some information will never make it back. For a human mission, that limited bandwidth is a serious constraint. You want constant health monitoring, high-resolution imagery of the ship and the surroundings, science data, and regular communication between the crew and their families. Each of those streams eats into a very small data budget. You are constantly deciding what matters most, what can wait, and what will not be sent at all. And if something goes wrong, getting full diagnostic data back to Earth in a hurry is not as simple as upload the log. On the ISS, the situation is completely different. Ground controllers can watch data almost in real time, see a problem as it starts, talk to the astronauts with only a tiny delay, and guide them through repairs. If an issue looks dangerous, there is at least the option to get the crew into a return vehicle and deorbit within hours. That feedback loop between crew and ground is part of the safety net. At Saturn distances, that safety net is ripped wide open. By the time Mission Control hears we have a problem, that problem has already been happening for more than an hour. By the time they analyse the data and send advice, another hour or more has passed. If the issue is time critical, like a leak, a fire, a rapid loss of pressure, or a serious power failure, the window to act may be shorter than the communication delay itself. The crew has to diagnose, decide, and execute fixes largely on their own, with only delayed support from Earth. So now combine everything. Navigation that demands millimeter per second precision over years, communication that crawls with huge delays and low bandwidth, a radiation-soaked, freezing environment powered by nuclear systems, and a crew whose bodies and minds are under constant stress. And after all of that, when you finally reach Saturn, you hit another wall, because getting there is only half the job. You then have to slow down enough to stay. Falling toward a gas giant at tens of kilometers per second is one thing, but slamming on the brakes without killing the mission or the crew is a whole new layer of risk. Getting to Saturn is easy compared to stopping there, and that sounds insane until you look at the numbers. Falling toward a giant planet is simple. Gravity does the work for you. The real nightmare is what happens at the end, when you're racing in at extreme speed and you have to decide right now, are you going to stay, or are you going to sling past Saturn forever? By the time a spacecraft reaches Saturn, it has been falling inward or outward through the Sun's gravity well for years. Relative to Saturn, you can easily be moving at tens of kilometers per second, that's tens of thousands of meters every second, on the order of 70,000 to 90,000 miles per hour. Saturn itself has an escape velocity of about 36 kilometers per second at the cloud tops, around 22 miles per second. If your arrival speed is high and you do not slow down enough, Saturn's gravity just bends your path and throws you back out into deep space. You get a flyby, some data, and then the planet is gone behind you permanently. For an orbit, you must pay a huge braking bill. You have to remove a big chunk of that arrival speed so that your trajectory curves into a bound path instead of a one-time swing past. That is where the orbit insertion burn comes in, and for a gas giant like Saturn, that burn is long, critical and unforgiving. Look at Cassini. When it arrived at Saturn, it had to fire its main engine for about 96 minutes straight to slow down enough to be captured. Almost an hour and a half of continuous burn, with the entire mission hanging on that engine doing exactly what it was designed to do. If the engine had failed halfway through, or if the guidance had gone wrong, Cassini would have either skimmed past Saturn and escaped, or dived too deep and been lost. That was for a robotic probe weighing a few tons. Now scale that problem up to a human spacecraft with a massive habitat, shielding supplies and possibly landers for the moons. Your arrival mass is far larger, your speed relative to Saturn is similar or higher, and your required change in velocity is even bigger. You either need a much more powerful propulsion system, a much longer burn, or some advanced trick like Aerocapture. Each option multiplies risk in a different way. Aerocapture sounds brilliant on paper. Instead of burning huge amounts of fuel, you dive into the upper layers of Saturn's atmosphere at maybe 30 to 40 kilometers per second, roughly 70,000 to 90,000 miles per hour, and you let drag do much of the braking for you. You come in on a carefully chosen path, let the atmosphere slow you down, and then you pull back out into orbit. In theory, you save a huge amount of propellant. In practice, it is terrifying. Saturn is a gas giant with a deep, layered atmosphere that is not perfectly mapped. Density changes with height, latitude, weather, and time. At those speeds, a small error in how dense you think the area is can be deadly. If the atmosphere is thicker than expected at your entry height, heating and forces spike, you overheat the heat shield and the structure, and you risk burning or breaking the spacecraft. If it is thinner than expected, you do not slow down enough, and you skip back out into space, having thrown away your best capture chance. For a robot, maybe you accept that risk on an experimental mission. For humans, asking a crew to ride a thin shell through a barely known gas giant atmosphere at tens of kilometers per second is a very hard sell. The safer path, purely in engineering terms, is to use engines and carry the fuel to brake. But that brings you right back into the mass problem. To guarantee that you can not only capture into orbit around Saturn, but also adjust that orbit, move between moons, and maybe leave Saturn again for a return trip, you must carry a large propellant reserve all the way from Earth. That fuel sits in tanks for years while you cruise through space. It does nothing for you until the moment you need it, but you still had to launch it out of Earth's gravity well and accelerate it the whole way. For almost the entire mission, it is dead weight. Mission designers cannot ignore that. They have to size the launch system, the stages, and even the number of launches based on that braking requirement. If you decide you want generous safety margins at Saturn, your propellant load grows, your initial mass explodes, and your launch architecture becomes more and more extreme. If you cut propellant to make the rocket smaller, you reduce your options at Saturn and raise the risk that one unexpected event during insertion leaves you with not enough delta V to fix it. In the end, a lot of the story comes down to a single event, one major insertion burn. You spend 6 or 7 years cruising from Earth to Saturn, running checks, trimming your path, keeping the ship alive, and then you reach the critical point. You fire the main engine, you commit to the burn, and for tens of minutes or longer, you ride that thrust. If everything goes right, your trajectory bends, your speed drops, and you fall into a stable orbit. If anything serious goes wrong, there are almost no second chances. You're moving too fast, too close to a huge planet, with too little time and too little fuel to improvise. For a robotic mission, that is already intense. For a human mission, the risk profile is brutal. That one burn decides whether years of work and billions of dollars end in a functional Saturn outpost, or in a high-speed flyby with a lost crew and a broken civilization's confidence. You cannot repeat the launch tomorrow. You cannot rerun the arrival next year. The whole sequence is unique. So now put yourself in that situation. You have fought distance, you have endured radiation and isolation, you have managed navigation with hour-long delays, and you have survived a high-stakes braking maneuver at a gas giant. You are finally in the Saturn system. But here is the twist. There is still nowhere nice to go. The planet itself is a ball of gas you cannot land on, and the places you can land, the moons, are not cozy worlds waiting to welcome you. They are extreme environments with their own problems, from freezing lakes of methane to almost zero-gravity ice balls. If stopping at Saturn is that hard, what does it actually look like to try to live on or around one of its moons, where everything from gravity to atmosphere to surface material is working against the idea of a safe, stable human base? Even if you make it to Saturn, its moons are not friendly ports. They are exotic death traps that just happen to be scientifically fascinating. From far away they look like perfect real estate for a base, solid surfaces, lower gravity, some even have atmospheres. Up close, every single one hits you with a different way to make human life almost impossible. Take Titan first, because it sounds like the most promising. Titan is strange because in some ways it looks like a frozen version of Earth. It has a thick atmosphere, mostly nitrogen like ours. Surface pressure is about 1.5 times Earth's, so standing there would feel like being a little underwater in terms of pressure, not like standing in a vacuum. It has rivers, lakes and seas, but those are not made of water. They are made of liquid methane and ethane. The temperature on the surface is around 94 Kelvin, that's about minus 179 degrees Celsius, around minus 290 Fahrenheit. At that temperature, water is solid rock and methane is a liquid. That means your suit is not just fighting vacuum like on the moon, it is fighting a dense, cold hydrocarbon atmosphere. The outer layers have to survive contact with very cold, potentially sticky organic stuff while holding in warm, breathable air. Any leak, any crack, and that cryogenic air hits your equipment and your skin. Metals shrink, plastics turn brittle, seals harden. Your visor and joints have to work in thick, cold air, filled with small particles and droplets. Every system, from life support to communications, must be designed for an environment where everything around you is trying to freeze, crack, or dissolve Earth-style materials. Then look at Enceladus, the little moon that throws water into space. It is only about 500 kilometers across, tiny compared to our moon. The surface gravity is about 1% of Earth's. If you weigh 70 kilograms on Earth, on Enceladus you would feel like you weigh less than 1 kilogram, a fraction. That sounds nice for lifting things, but for human health over months or years, it is terrible. Your bones and muscles barely feel any load. Your cardiovascular system barely has to push. We already know from microgravity on the ISS that this leads to muscle wasting, bone loss, and heart deconditioning. 1% of Earth gravity is not enough to protect you. On top of that, Enceladus constantly shoots jets of water vapor and ice grains from its south polar region, making huge plumes that reach into space. Those plumes are great for science. They tell us about a possible subsurface ocean. But for machinery and unprotected humans, that environment is harsh. Ice grains can sandblast surfaces, clog moving parts and coat sensors. Passing through the plume means flying your hardware through a constant stream of cold particles at high speed. Standing or operating near active vent regions means dealing with surface instability, fresh deposits, and unpredictable jets. Other moons do not give you a break either, they just change the problem. Some inner moons sit deeper inside Saturn's radiation environment, so their surfaces are hit by higher levels of charged particles. That means any long-term stay increases radiation dose, again forcing you to bring more shielding, or bury your base under local material. Some outer moons are dark, cold, and irregularly shaped. They are not nice, smooth spheres. They are more like lumpy rocks. The gravity on these bodies is so weak that landing on them is more like carefully matching their motion and touching them very, very gently. A small mistake in speed or angle can send you bouncing off or sinking into loose material. In microgravity or near microgravity, basic movement becomes dangerous. The surface regolith on many icy moons is not soft powder, it can be sharp, jagged ice grains. That stuff can chew up seals, joints and treads. It gets into mechanisms, abrade surfaces, and makes dust control a full-time job. When you walk, even a small push against the ground can send you floating up and away for meters, because the gravity cannot pull you back down quickly. Every step, every jump has to be planned and practiced, or a small stumble can launch you off the surface in slow motion. Now add hidden hazards, things you cannot see with a quick look. Under a thin crust, there might be pockets of weaker material, voids, or fractures. A heavy lander setting down in the wrong place could crack through and tilt or sink. Rovers could break through unstable layers. You're trying to operate heavy, complex machines on terrain no human has ever walked, where your maps are made from remote sensing data with limited resolution. Then there is planetary protection, which most people do not think about. But for moons like Enceladus and Titan, it becomes a big deal. If there is liquid water under the ice or complex chemistry on the surface, there is at least a chance, even if it is small, that some kind of primitive life or pre-life chemistry exists there. You do not want to dump Earth microbes into that environment and wipe out or contaminate whatever is there. At the same time, if there is alien biology, you do not want to bring it back into your habitat or onto Earth without strict control. So every lander, every tool, every sample container has to be sterilized to a high standard. You need airlocks, containment protocols, decontamination procedures. Suits have to be cleaned, samples have to be sealed properly. Waste from the crew has to be managed so it does not leak into the local environment. That adds more systems, more steps, more time, more mass. The more interesting a moon is scientifically, the more careful you have to be and the harder it gets to just live there like a base. Put this together and the picture is clear. Titan, Enceladus, and the rest are not future suburbs of humanity. They are extreme labs, where everything from gravity and temperature to chemistry and surface structure is hostile to long-term normal human life. You're trying to build fragile islands of Earth like conditions in places that were never meant to support them. And every island has to be supported by a huge logistics chain stretching all the way back to Earth. And even if you somehow manage all of that, there is one more trap waiting for you in the Saturn system, something that looks beautiful and calm from a distance, something that's been on posters and screensavers for decades, but up close is just another way to tear a spacecraft apart. The rings look like a cosmic highway, thin, bright and smooth, but if you try to treat them like a safe route or a parking spot, you find out very fast they behave more like a giant slow-motion shredding machine. The rings look like a cosmic highway, but up close they behave more like a slow-motion sandblaster. From far away they look thin, clean, almost flat, like you could just slide a ship through them and enjoy the view. In reality, when you fly near the rings, you are moving into a three-dimensional swarm of projectiles. Saturn's rings are not a solid disk. They are made of countless separate pieces. Most of that material is water ice with some dust and rock mixed in. The sizes range from tiny grains a few micrometers across, smaller than dust in your house, all the way up to chunks the size of boulders, tens of meters wide. You're not looking at a smooth sheet, you are looking at an insanely crowded collection of ice and rock, each piece in its own orbit, each one with its own speed and direction, all controlled by gravity and collisions, not by you. Here is the key problem. Even if your spacecraft matches the average orbital speed of the ring material at a certain radius, not every particle around you is moving at that exact speed and angle. Locally, some pieces are on slightly higher or lower orbits, some are tilted, some are bouncing from recent collisions. That means that relative to your ship, individual particles can still slam into you at tens to hundreds of meters per second. That is tens to hundreds of kilometers per hour, or tens to hundreds of miles per hour. Now imagine a grain of ice the size of a marble, a couple of centimeters across. At those impact speeds, the energy in that tiny piece is enough to punch through thin metal, crack a window, or damage a radiator. Scale that up to a piece the size of a fist or a brick, and you're looking at a hit that can rip through structural elements. Your hull cannot be airplane skin thin in that environment. You either carry heavy shielding, which adds mass and hurts your delta V, or you accept a rising risk of serious damage every time you pass through ring material. Cassini showed how serious this is. When NASA sent it into the Saturn system, engineers did not just fly it straight through dense ring regions and hope for the best. They chose narrow gaps, places where the density of particles was relatively low, and even then they pointed the high-gain antenna in the direction of motion to act as a crude shield. They relied on careful modelling, good luck, and the fact that Cassini was an unmanned probe that could afford some risk. Even in those safe passes, there was a chance of impacts that could have damaged instruments. Now, take that experience and think about a large human-rated ship. The cross-section of the vehicle and the area it presents to oncoming particles is far bigger than a compact probe. There are more surfaces to hit, more external structures like antennas, radiators, and docking ports, and a pressurized habitat where any puncture is life-threatening. The number of particles you intercept goes up with your size, so your overall collision risk climbs. To bring that risk down, you would have to design heavy armor around key areas or adopt extremely conservative paths that avoid ring plane crossings as much as possible. Both choices come with costs, and forget the idea of parking in the rings. There is no stable patch where you can drop a habitat and let it sit like a building on a foundation. Every ring particle is in orbit, every piece is moving, and collisions are constantly reshaping the structure. Bits of ice collide, stick, break apart, and shift orbits. Gravity from Saturn and the moons continually tugs on ring material, creating waves, gaps, and clumps. If you tried to anchor a platform directly inside this environment, it would be hammered by ongoing impacts and dragged around by local mass changes. To stay in a specific configuration, you would need continuous station keeping, active thrusters, and constant monitoring, on top of thick shielding and aggressive dust mitigation systems. Even if you stay outside the densest parts, the rings restrict your freedom to maneuver. Many of Saturn's moons orbit outside the main rings, but their paths and inclinations still relate to the ring plane. If you want to move a human ship from one moon to another, especially if their orbits cross the ring plane, you have to plan trajectories that either thread through the cleanest gaps or go up and over the ring region entirely. Every time you avoid a dangerous crossing, you spend extra delta V. Every time you accept a crossing, you accept impact risk. That shrinks your list of good paths and complicates your mission design. For robotic probes, you can accept a higher chance of damage to gain better science, like Cassini did when it flew risky paths in its final orbits. For humans, that trade is very different. One unlucky piece of ice hitting a radiator, a propellant line, or part of the pressure hull can turn into a critical emergency. And remember, at Saturn distances, there is no fast rescue and no live help from Earth. The rings become a hazard zone you mostly route around, not a scenic lane you casually cruise through. So now step back and look at what Saturn is offering you. A planet you cannot land on, moons that are extreme environments, a ring system that behaves like a giant debris field, radiation belts, deep cold, weak sunlight, and brutal delta V requirements. You can, in theory, design around each of these, but every fix adds mass, cost, complexity, and time. At some point, the question stops being is it possible at all and turns into who is going to pay for this and for how long, and what do they cancel to make it happen? If the physics doesn't quite kill your Saturn dream, the price tags step in and finish the job, because building a human Saturn mission is not just an engineering problem, it is a civilization-level budget decision that has to survive decades of changing priorities. Even if physics allowed a human trip to Saturn, your economy probably will not, and this is where the dream hits a different kind of wall. Up to now, we have talked about distance, radiation, propulsion, navigation, all the hard physical limits. But there is another limit that is just as real: money and will. You can engineer your way around many technical problems if you are willing to spend enough for long enough. The question is, will anyone actually pay that bill and keep paying it for decades? You already have a rough template for what serious human space projects cost. The Apollo program, which sent 12 people to the moon, cost on the order of $25 billion in the 1960s. Adjust that to today's economy, and you are looking at hundreds of billions. The International Space Station, built and operated over decades, is also in that same broad cost range. Those programs were focused on relatively near targets. The Moon at about 384,000 kilometers and low Earth orbit at a few hundred kilometers up. Now take everything Apollo and ISS had to do, and imagine stacking decades of deep space operations, nuclear power systems, heavy shielding and interplanetary logistics on top just to get a handful of people into the Saturn system once. A Saturn mission will not be one big heroic launch from a single giant rocket. The mass you need to move is simply too large. You are talking about a multi-launch mega architecture. Several, maybe dozens, of heavy lift launches to low Earth orbit, orbital assembly of the main ship like building a small station in space, fuel depots either in Earth orbit or somewhere further out, to refuel transfer stages, nuclear stages for power and maybe propulsion, precursor robotic missions to scout trajectories, test Aerocapture, or validate radiation environments. Each of those steps is its own project, with design teams, test programs, risk, and a large budget line attached. That kind of architecture spreads cost over many years and over many different parts of the space agency and its partners. On paper, that sounds manageable. You just phase it. Saturn mission timelines are not 10 years. They are 20 to 30 years from first serious concept of first human flyby or orbital stay, and longer if you want a decent chance of a safe return and long-duration operations there. You're asking multiple generations of taxpayers and agency leaders to keep supporting a single, extremely expensive goal that does not pay off in visible results for decades. History shows what usually happens. Big programs get cancelled, renamed, or redirected. One administration wants Mars, another wants the Moon, another wants commercial low Earth orbit, and each one cuts or reshapes the previous plans. Budgets get squeezed by recessions, wars, and domestic priorities. Long before your Saturn vehicle is fully assembled, some future decision maker looks at the line items and asks, why are we spending this much on a distant gas giant when we have closer goals and more pressing needs? And that leads to the brutal concept of opportunity cost. Every billion you put into a Saturn program is a billion you're not using for Earth observation satellites that track climate and weather, or for Mars missions that are actually within near-term reach, or for lunar infrastructure that can support multiple programs, or for large telescopes that can look deep into the universe without risking human lives. When you have finite funding, you cannot do everything at once. Saturn is far hard and has very little direct economic payoff. Mars, the Moon, and low Earth orbit have clearer links to future industry, science return per dollar, and national prestige. In that kind of budget fight, Saturn loses. If you ask a scientific panel, what should we fund with limited money, they will say, build more observatories, send more robotic orbiters and landers, expand Mars exploration, improve Earth monitoring. Humans at Saturn fall off the list quickly, not because it is not interesting, but because it is an extremely inefficient way to get science. That brings us to the last point, robots. Robotic missions give you a huge fraction of the science for a small fraction of the cost. Cassini and Huygens together deliver detailed maps, atmospheric data, magnetic field studies, images, and even a landing on Titan, all without having to keep humans alive out there. Pioneer 11 and Voyager 1 and 2 flew past and returned critical information on Saturn's rings, atmosphere, and moons. Future orbiters, landers, and maybe even drones or submarines for Titan's lakes or Enceladus's plumes can be built for costs that, while large, are still vastly lower than a full human deep space program. From a science per dollar perspective, unmanned probes are simply better. They do not need air, water, food, gravity, or protection from microgravity muscle loss. They can tolerate higher radiation levels and colder temperatures. They can stay in hibernation for years without complaining. They can fail without triggering a national trauma over lost lives. As long as machines can do almost all the measurements and observations that scientists want at Saturn, a human mission looks less like a rational research project and more like an extravagant stunt. So combine all the factors: extreme distance, brutal delta V, deep space radiation, cryogenic temperatures, weak sunlight, delicate navigation, dangerous rings, harsh moons, and then paste a price tag on top that likely climbs into the many hundreds of billions over decades, with no guarantee of stability. The result is simple. On paper, you might squeeze out a technically possible Saturn mission, but in practice, in the world you actually live in, that mission is a fantasy. It does not fit easily into any country's budget, attention span, or risk tolerance. And yet, even if someone wrote the check and somehow the program survived, there is still one more obstacle that is not just about money or technology. It is about time. Human lives, careers, and skill sets have limits. A Saturn mission does not just stretch your rockets and your budgets, it stretches your timelines to the point where a single human lifetime barely fits around the project. So the next question is simple and uncomfortable. What happens when the mission you're planning takes so long that the people who start it will be old or gone by the time it reaches Saturn, and the crew you send will spend a major chunk of their own lives just getting there and back? Saturn is so far and so complex that a single human career barely fits the project, and that breaks more than your schedule. It breaks how your whole system normally does engineering and exploration. You're used to missions where the people who design the hardware are still around when it flies, still around when the data comes back. With Saturn, that nice loop starts to stretch until it snaps. Think about the timeline in simple steps. First, you have to design the mission architecture, pick propulsion, life support, shielding, trajectories, assembly methods. Then you actually build and test the hardware, which for something this complex is not quick. Realistically, you could easily spend 10 to 15 years just on design, development, prototyping, testing, and fixing all the issues that show up. Big rockets slip, new reactors slip, life support systems slip, simulators, training, ground support, all of that takes time. Then after all that, you finally launch. Now the ship starts its cruise to Saturn, and you're not talking months, you're talking about 6 to 8 years of flight time, maybe more if you rely heavily on gravity assists. Add it up, and you're looking at more than 20 years between serious kickoff and first human arrival at Saturn, and that is if everything goes right the first time. No major accidents, no big redesigns, no long pauses for budget problems. Now look at technology over a similar 20-year span in your normal life. Think about what computers, software, and communications looked like 20 years ago compared to now. Phones, laptops, networks, all changed beyond recognition. For a Saturn ship, you cannot keep updating the design every time something new comes out, or you never finish. At some point, years before launch, you have to freeze the design. You pick a generation of computers, a type of processor, a software stack, a communication standard, and you lock it in. By the time the ship is actually coasting towards Saturn, that hardware is already behind what exists on Earth. By the time it arrives, it is ancient. Mid-flight upgrades are not simple. You cannot just patch in a new processor the way you swap a phone. Every system in the ship is tested as a whole. Wires, power supplies, cooling, software, all tuned around the original design. Changing a major component in the middle of a mission means retesting interactions you cannot retest in full. So you live with what you launched. If a vulnerability or design flaw shows up, you patch around it in software or procedures, but you do not change the core architecture. You ride an obsolete computer system into one of the most demanding environments in the solar system, because upgrading halfway is closer to science fiction than to safe engineering. Now put people on board that system and stretch their lives across that timeline. Say you pick a highly trained crew in their early or mid-30s. They train for several years before launch. They fly a mission that lasts maybe 10 to 12 years end-to-end, including pre-departure quarantine, outbound crews, operations in the Saturn system, and return. If they come back, they're in their mid-40s to 50s. That is a huge chunk of a person's working life tied up in one mission. And this is not 10 normal years. These are years spent in microgravity or very low gravity, under constant radiation exposure, with chronic stress, limited movement, and no real emergency exit. You already know that months on the ISS can cause bone loss, muscle shrinking, and changes in vision and the cardiovascular system. Now extend the exposure to many years and add deep space radiation on top. You are not just sending these people on a trip, you are deliberately putting them into an accelerated aging experiment. Their bones, hearts, blood vessels, and nervous systems all take hits that may not fully recover, even after return. On the ground, the program itself has to outlive individual careers. A realistic Saturn program is not one clean arc, it is layers. One generation designs the overall concept and begins building the infrastructure. Another generation finishes the hardware, conducts the launch campaign, and runs the mission during cruise and early operations. A third generation might be handling late-stage operations, data analysis, and any follow-up missions or rescue attempts if something goes wrong. Every time responsibility passes from one group to another, you risk losing expertise. People retire, move, or die. Documents get archived poorly. Software tools change. The original tribal knowledge about why certain decisions were made fades. On top of that, every generational handoff has to survive budget reviews. A new leadership team can decide that the old project is too expensive or that new priorities matter more. So while you are trying to keep a fragile chain of technical knowledge intact, you're also trying to keep a fragile chain of institutional support intact. Both can snap. Then you have the problem no one likes to talk about honestly. The longer a project runs, the more chances there are for something big to go wrong. Over a span of 20 to 30 years, the probability that you will see at least one major disruption moves toward almost guaranteed. That disruption could be a launch failure that destroys a key piece of hardware. It could be a serious system breakdown discovered late in testing that forces a major redesign. It could be an economic crisis that slashes budgets. Planning for that level of resilience is a huge project by itself. You need backup hardware for things that are too expensive to build twice. You need alternative suppliers in case one fails. You need contingency plans for schedule slips, cost growth, and partial failures in space. Every layer of insurance costs more money and time, and you never reach a point where risk is zero. You're just trying to keep it below a threshold that agencies and the public will tolerate. So when you add time to all the other factors, Saturn stops looking like a big mission and starts looking like a multi-decade commitment that strains technical systems, human health, institutional memory, and patience all at once. It is not just that the planet is far away, it is that the journey competes with the length of a human working life and the stability of your institutions. And yet, even if you accept all of that, there is still another layer that makes the whole thing feel out of reach. A lot of the hardware you would really want for a safe, efficient Saturn mission simply does not exist yet in proven form. You can sketch it in presentations, you can simulate it on computers, but you cannot buy it, test it, and fly it today. You are missing technologies you do not just want, you probably absolutely need. So the next question is, how do you send humans to Saturn safely when the life support, artificial gravity, nuclear power, and high-efficiency propulsion systems you really need are still mostly ideas, prototypes, or short-duration demos rather than trusted, decade-long workhorses? To take humans to Saturn safely, you need hardware that does not exist outside presentations and concept art, and that's a huge problem people tend to gloss over. On paper, you can always say, we'll just improve the tech, but when you look at what you actually need, you realize you're missing entire classes of machines that are nowhere near ready for decade-long deep space service. Start with life support. Right now on the ISS, we recycle a good amount of water and some of the air. We reclaim humidity from breath and sweat. We scrub carbon dioxide, we recover urine water. These systems are designed for missions measured in months to a few years, with constant resupply from Earth and the option to send up replacement hardware. For Saturn, that is nowhere near enough. You are not just recycling for a short stay, you want near-perfect recycling of water, oxygen, and eventually nutrients for 10 years or more without regular shipments from home. That means a closed-loop system that can handle all the crew's waste, break it down safely, reuse the elements, and keep doing that non-stop. It has to tolerate hardware failures, contamination, biofilm growth in pipes, sensor drift, and still keep output within safe ranges. It also has to be repairable with tools and spare parts you carry on board, because there is no warehouse in orbit around Saturn. We do not have a proven, full-scale, decade-tested system like that. We have pieces, experiments, and partial loops, not a fully closed ecosystem you'd trust with human lives that far away. Then there is gravity. You already know years in microgravity are not acceptable for a Saturn crew. Bone loss, muscle wasting, heart and blood vessel changes, balance and vision issues all get worse with time. The usual proposed fix is done called artificial gravity by rotation. Spin the habitat so that centrifugal force pushes people down toward the outer wall. In simple terms, you build a big rotating ring or drum, and the crew lives on the inside surface. But to make that comfortable and safe, you need a structure that is tens of meters across, maybe more, spinning at carefully controlled rates. Spin too fast with a small radius and people feel sick because their inner ears notice the rotation. Spin slower with a large radius and it's more comfortable, but the structure becomes huge and hard to build. We have never constructed, spun up, and operated a large rotating habitat in space, not even close. We do not have tested bearings for that scale in vacuum, long-life slip rings or wireless power transfer schemes for rotating sections, or a playbook for how to safely dock vehicles to a spinning station in deep space. All of that has to be invented, tested in Earth orbit, and then scaled up for Saturn. Next, power. A human Saturn vehicle is not running on a couple of solar panels and batteries. At 9 to 10 astronomical units from the Sun, solar power is so weak that large, practical human missions basically have to go nuclear, and not with small, low-power sources. You're looking at megawatts of electrical power if you want strong electric propulsion, robust habitats, maybe rotating gravity sections, and multiple backup systems. That implies full-scale, space-qualified nuclear reactors that can run for decades without a maintenance crew. Right now, we have only tested small kilowatt-scale space reactor concepts and flown radioisotope generators that deliver hundreds of watts. That is 3 or 4 orders of magnitude below what a serious Saturn ship might want. A megawatt-class space reactor has to be launched safely, shielded from the crew, cooled by the large radiators, protected from impacts, and controlled by electronics that themselves have to survive radiation. It has to start up in space and then run for many years without a repair shop. That is a very different challenge from running a power plant on Earth, where you can send technicians in trucks. Now look at propulsion. Chemical rockets can get you to Saturn, given enough fuel and time, but they make everything heavy and slow. To cut travel time and reduce the amount of propellant you need, you want high-efficiency propulsion. Nuclear thermal rockets that heat hydrogen to very high temperatures and throw it out this back at high speed, or powerful electric propulsion system, like ion or Hall thrusters, scaled up massively. Nuclear thermal rockets could give you about double the performance of the best chemical engines, maybe more. Electric thrusters can be even more efficient, but they need large amounts of electrical power and usually produce low thrust over long durations. The problem is, none of these are flying at Saturn mission scale. Nuclear thermal rockets have been tested on the ground in the past but never flown in space. High-power electric propulsion is being developed, but current systems are used on relatively small satellites and probes, not multi-hundred-ton crewed ships. The idea of a megawatt electric propulsion stage pushing a large habitat on a multi-year trip is still in the future tech bucket, not on the launch pad. Before you bet human lives on it, you'd have to run full-scale demos closer to home, probably over many years. Finally, there is the basic durability of the spacecraft itself. On a 10-year mission, something major will fail. Not might will. Electronics will age. Mechanical parts will wear. Seals will leak. Software bugs will show up in situations you never simulated. If you want the ship to stay alive without direct help, you need deep autonomy, systems that can diagnose their own problems, reconfigure themselves around failures, and in some cases physically repair or replace components. That means modular hardware, where a robot arm or a crew member can swap out a box or a panel without ripping the whole ship apart. It means built-in diagnostic sensors, smart software that watches for early signs of trouble, and maintenance procedures that can be done entirely with what you have on board. It also likely means robotic assistance inside and outside the ship, handling tasks that are too dangerous or too repetitive for humans in suits. Right now, we are only starting to see this level of autonomy and modularity in smaller ways on satellites that can replace limited units or reconfigure their software. A fully self-repairing, self-diagnosing, human-rated Saturn ship is still a long step beyond that. So when you put all this together, you see the real picture. It is not just that our rockets are a bit weak or our shields a bit thin. The whole stack of required technology, from life support and artificial gravity to high-power reactors, advanced propulsion, and autonomous maintenance, is incomplete. Each piece is in progress or on the drawing board, but not yet bolted together into something you would trust for a decade in deep space. And this leads to a natural reaction, a kind of escape fantasy where people say, fine, if chemical rockets, rotating habitats, and normal reactors are too primitive, we'll just jump ahead to something crazy fast. A fusion drive, an antimatter drive, even a warp drive. But that runs into another hard wall, because those future drives are either still primitive concepts or pure speculation, and they do not magically erase all the other limits you've run into. So the next question is, if you try to fix Saturn with exotic engines and cutting-edge propulsion, do you actually solve the problem? Or do you just swap one set of impossible requirements for another? You might think, fine, we'll just invent a crazy fast engine and blow past all these problems, but physics has very firm opinions about that, and most of the flashy solutions you see online are either immature or almost completely speculative. Faster engines can help, but they do not magically turn Saturn into an easy weekend target. Start with something that actually fits inside known engineering: nuclear thermal rockets. The idea is simple in principle. You run hydrogen through a very hot nuclear reactor, heat it until it scrims out of the nozzle at very high speed, and you get an efficiency roughly double that of the best chemical rockets. That means a higher exhaust speed, shorter trip times, and less propellant for the same change in speed. On paper, that's exactly what you want for Saturn, because it attacks the fuel problem directly. But here's the reality. We have tested nuclear thermal engines on the ground decades ago, and we have talked about new ones, but we have never flown a nuclear thermal rocket in space, not once. We have never trusted one with a human crew, never run one for years, never used one for repeated big burns on a decade-long mission. Before you strap people to that system and send it out of the solar system's safe zone, you would need a whole program of test flights in Earth orbit and cislunar space, plus long-duration demos. That is years to decades of extra work before you even start the Saturn countdown. Then there is nuclear electric propulsion, which sounds even more attractive. Ion drives and Hall thrusters throw ions out the back at tens of kilometers per second, far faster than chemical exhaust. They're extremely efficient in terms of propellant use. The catch is thrust. They push very gently. Current ion drives deliver tiny forces, fine for small probes but useless for quickly moving a huge, crewed ship. To push a big Saturn vehicle with meaningful acceleration, you would need megawatts of electrical power feeding large arrays of thrusters. That loops you right back to the problem you already do not have solved: big, long-life nuclear reactors in space. Without a reactor that can steadily produce megawatts for years, nuclear electric propulsion stays stuck in the great for small probes, not enough for heavy crews category. Next comes the one everyone likes to bring up: fusion. Fusion drives are shown in art, games, and sci-fi all the time. In theory, they could heat propellant to insane temperatures, giving incredibly high exhaust speeds and huge performance. But controlled fusion for basic power plants on Earth is already a serious challenge. We still do not have commercial fusion power stations feeding a grid. Now imagine shrinking a fusion reactor, making it light enough for a spacecraft, making it stable enough to run for years, and making all the support systems work in vacuum, under radiation, with no maintenance crew. Right now, fusion propulsion is mostly a set of good-looking plots, nice simulations, and artist impressions. It is not a tested, flight-ready engine you can buy and bolt onto a rocket. If you go even more extreme into antimatter and warp drives, things get worse, not better. Antimatter contains ridiculous amounts of energy per kilogram when it annihilates with normal matter. In theory, a few grams could power very powerful engines. In practice, producing even nanograms of antimatter takes enormous amounts of energy and money in particle accelerators, and storing it safely is a nightmare, because it destroys any normal container it touches. You end up needing complex magnetic traps, ultra-high vacuum and perfect control, and even then the risk of catastrophic release is huge. That is not something you want near a crewed ship or near a planet. Warp drives and Alcubierre type concepts are even further out. They rely on distortions of space-time that require exotic matter, negative energy densities, or conditions that either break known physics or demand resources on the scale of stars. Even if small tweaks to the theory reduce those demands, you're still nowhere near hardware. These ideas sit in theoretical papers and thought experiments, not in engineering labs building engines for test stands. The key point is this: even if you gave yourself a generous, advanced but realistic engine, like a mature nuclear thermal rocket or a megawatt nuclear electric system, you would not erase all the other limits. Say you cut the transit time to Saturn from 7 years down to 2. That is a big improvement, but what is still true? You still have deep space radiation from cosmic rays and solar storms for years. You still have to carry or recycle air, water and food. You still face microgravity problems unless you build artificial gravity. You still have huge communication delays, on the order of an hour and more one way. You still have to slow down at Saturn, either with a giant burn or a risky Aerocapture pass. You still have to operate in a magnetosphere in deep cold near dangerous rings and extreme moons. Faster engines shrink one dimension of the problem, travel time, but they do not change the fact that Saturn is far, harsh and expensive in every other way. You are still fighting the rocket equation, just with a slightly better number in one spot. You still need reactors, radiators, shielding, rotating habitats, autonomous repair systems, and a budget that stays alive for decades. Advanced drives make the numbers a bit less brutal, but they do not turn the mission into something easy, routine, or cheap. So when you add it all up, you get a sobering conclusion. Physics does not absolutely forbid humans at Saturn, but it does not welcome them either. It lets the mission exist on paper, at the cost of enormous complexity, serious risk, and extreme expense. And that raises one last very simple question, which cuts through everything. If Saturn is this hard for you, who actually gets to go there in reality? You personally, or your machines? Saturn isn't absolutely unreachable, but for you it may as well be. That's the uncomfortable truth under all of this. The solar system has already proven that you can reach Saturn, sample it, photograph it, and even land on one of its moons. You've already done the Saturn mission, just not with a heartbeat on board. Look at the record. Pioneer 11 flew by Saturn. Voyager 1 and Voyager 2 both passed it, grabbed images, measured fields and particles, and then kept going out of the solar system. Cassini spent more than a decade orbiting Saturn, mapping the rings, the atmosphere and the moons, looping through the system again and again. The Huygens probe detached from Cassini and dropped through Titan's atmosphere, landing on its frozen hydrocarbon-soaked surface and sending back images from the ground. So yes, Saturn is reachable. If you're a hardened machine that does not need air, gravity, food or comfort, and that no one expects to bring home. The reason that works is simple. A robotic probe can be small and tough. Cassini, fully fueled, was on the order of a few tons. It could survive deep cold with electric heaters, take radiation hits that would be dangerous to humans, and run on a few hundred watts of power from radioisotope generators. It did not care about microgravity bone loss. It did not care about isolation. It did not care that light took more than an hour to cross the gap. If a system started to degrade after 10 years, that was acceptable, because the hardware had already done its main job. Now try scaling that to a human mission, and you break the whole equation. You're not sending a 3 to 6 ton robot anymore, You are sending perhaps hundreds of tons of hardware. You need a pressurized habitat with multiple rooms, shielding against radiation, food, water and oxygen for many years, exercise equipment, medical gear, spare parts, landers or transfer vehicles for the moons, and heavy propulsion and power systems to move it all. The same 1.4 billion kilometre distance, around 870 million miles, that a small robot crosses with a modest propellant load turns into a monstrosity of mass and cost when you add human needs. And you have to be honest about the scale of the playground you're in. Saturn, at about 1.4 billion kilometres from the Sun, is only one step out. Beyond it sit Uranus, Neptune, the Kuiper Belt, and way beyond that the Oort cloud. The outer solar system is not just farther, it is vast in a way your normal life never deals with. Your cars, planes, and even your normal rockets are built for a tiny bubble around Earth, a bubble measured in thousands or maybe millions of kilometres. The structure of your economy, your technology, your launch systems, your supply chains, they're all tuned to that inner zone. Saturn sits far outside what your civilization is naturally built to handle. So when you say it's impossible to reach Saturn, what you really mean is not with the tools and systems we have now and not with the way we currently organise money and time. Physics does not strictly forbid a human Saturn mission. You could, in principle, stack enough stages, build nuclear reactors, spin huge habitats, and assemble a massive ship in orbit that can make the trip. If you solved radiation shielding, long-life reactors, closed-loop life support, and high-efficiency propulsion, you might get a crew there and back alive. But line that up against what you actually have today. Your rockets are mostly chemical, your reactors for space are small prototypes, your life support loops are partial and short-term, your artificial gravity experience is close to zero, and your budgets fight over every billion. None of that matches a 20 to 30-year, multi-hundred billion dollar high-risk program to send a handful of people to the Saturn system, keep them alive, and bring them home. For all practical purposes, in your lifetime, Saturn might as well sit behind a glass wall made of physics, engineering limits, and economics. You can see it through telescopes, you can send robots to touch it, but you, personally, will almost certainly never feel Titan's thick air on your suit, or see the rings from a habitat window with your own eyes. The door is not locked by some mystical force. It is locked by a combination of harsh numbers and human constraints. And that's the twist that makes Saturn so uncomfortable to think about. The reason it feels impossible is not that Saturn is some forbidden zone physics will never let you enter. It feels impossible because the planet brutally exposes the limits of what your species can do right now. Its distance shows where your propulsion and energy systems stop being effective. Its radiation belts and cold show where your shielding and material stop being practical. In that sense, Saturn is a mirror. One version of that mirror shows a future where you solved high-power nuclear reactors for space, built giant rotating habitats, mastered long-term life support, and made deep space travel something more than a one-off stunt. In that future, a human ship sliding into Saturn orbit is not a miracle. It is just a very hard job that your civilization knows how to do. The other version of the mirror shows a future where Saturn stays what it is to you now, a distant, beautiful place that only your robots ever touch, while you watch from home through images and data streams. Right now, everything you've built, every system you rely on, every budget line points much more toward that second future. Robots will keep going, they will keep diving through the rings, landing on Titan, sampling plumes from Enceladus, and mapping the moons in more and more detail. You will watch those missions with excitement. You will see the images and say we were there, but the we will mean your machines, not your bodies. So the real question hanging over Saturn is sharp and personal. Will your species decide to rebuild its technology, its infrastructure, and its priorities so deeply that a human Saturn mission becomes normal? Or will you accept that for you and for many generations, Saturn will remain something you only ever visit as a signal on a screen, a place that is technically reachable but practically out of reach? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.